Good afternoon, everyone, and it's a great honor to be here. We've had a mixture of speakers from governments, industry, and now academia. And as we go down the agenda, we become more and more concrete about the AI. So my hope is that I'll be able to enthuse you about the potential of hearables in this context. So, machine intelligence at Imperial. So Imperial College is a law institution, and the only reason my slide is about Imperial is that we have an intellectual capital. So in my view, you need to have very, very strong and long intellectual capital in your area, in your institution, in order to be able, as it were, to stand on the shoulders of the giants. So Denis Gabor was a Nobel Prize winner back in 1981 for holography. He derived his holography experiments and equations in 1945, 1946, but he didn't have the equipment to run the experiment. So not until the semiconductors and transistors, such like we introduced in the early 1960s, was he able to demonstrate his theory. So it took him 20 years before he introduced the theory and the time they introduced monochromatic lasers so he could prove his theory. Okay, fast forward a few years. These days we don't have such luxury. So working in engineering, in AI, you don't have the luxury to introduce your theories even 1 year before you prove them. And my talk is a lot about that. Okay, so we are witnessing the fourth industrial revolution. The first industrial revolution is maybe 80s, 70s with the steam engine, and so that steam engine allowed us to travel. Maybe there's some agriculture utility machines based on steam engines, like for harvesting and such like. The second industrial revolution here is mass production, so it's about electricity. So around 1900, it was possible to use electricity in industrial power plants. If you remember an old movie by Charlie Chaplin where he was on an assembly line, kind of turning some screws all the time, when he saw a lady during the break with 4 buttons, he ran after her to tighten the screws. Second industrial revolution, people are moving from villages to cities in order to work in factories. Third industrial revolution is about computers. So mid-1970s, especially the personal computer, where we started using digital technologies. And now witnessing the fourth industrial revolution. Some people call it AI. I prefer to call it cyber physical systems, where AI is one of the components of such systems. We have a very interesting phenomenon that with AI, people are actually moving from cities to towns and villages because we are all becoming digital nomads. So for my work, honestly, I love to talk to people, but if I'm fully focused, I can be anywhere in the world with the internet and my computer, and I can be equally productive. Okay, so AI for health. For many reasons, AI is almost fully untapped when it comes to health applications. So here, you have a very lovely chap. He's the real patient in one of the London hospitals. So he suffers from sleep apnea, which means he cannot sleep in the night. It's interrupted. So his life is misery because he can't sleep. Then his wife's life is misery because she can't sleep because he can't sleep. And to treat him, they take him to top hospital in London. Okay, so this lovely chap comes from his house, wherever his retirement home is, and they put some equipment on him, which consists of electroencephalogram, then electrocardiogram, respiration belt, turbulence flow, and chest strap for respiration recording. So he's supposed to sleep his normal sleep rhythm in a foreign, totally strange environment. Of course, he's not going to sleep his normal sleep cycle, so he's going to be diagnosed wrongly, and he's going to be treated wrongly. And many people experience that. So my dream ever since maybe 2008 or so was, how about using earplugs? Because it's very, very convenient. Also, the new generation are very much used to earplugs. If you look on the bus or tube, or tram, tube, metro, I live in London, we call metro tube, rail or wherever, people are wearing earplugs. Some people also wear hearing aids. So how about using that to maybe introduce sensing? Okay. So with an earplug, you could sleep at your home, your normal sleep cycle, and you could be diagnosed correctly and you can be treated correctly. Okay. So the first thing I did was very, very brave. If I was to do it right now, I would be much more careful. But when you have a new idea, you get very, very excited. So I thought a little bit about human anatomy. And if you want to record electroencephalogram from head, then this is brain. So from brain, the electric potential goes through the brain tissue, cerebrospinal fluid, which is conductive fluid between the brain and the skull. This is skull, the bone, and then skin. Okay, if you want to record from the ear canal, you have the same. Brain, cerebrospinal fluid, bone, skin, all conductive. So yeah, that's possible. The only problem is that this bone here that protects the ear canal is much, much thicker than skull. So your signal is weaker. So in principle, intuitively, I can record electroencephalogram, which is the key component for sleep staging, for scoring sleep. But my signal will be weaker. And to do that, I need to have an earplug, which I equip with some sensors, and I have some electronics, and I should be able to do that. Okay, so standard electroencephalography. So you have that cap with electrodes, and it takes 1 or 2 hours for a skilled person to put those electrodes. And that's all in the lab or in the clinic. By the time they put electrodes on you, and trust me, I've been there many times, you fall asleep. So you don't really give your very good normal brain responses. So how about replacing all that with an earplug? So the advantage would be that if you have sensors on an autonomous system on an earplug, you could administer it yourself. So you don't need to go to clinic. You can do it at home or in the community, as we say. And you're fully, fully independent. There's another interesting thing. When you have that EEG cap on the left, there's many, many leads, wires, leading from cap to the recording device and back. So those leads make a loop. That loop picks up the electric field, which means that you have many, many artifacts due to the external electric field, the basic induction. What happens with the ear canal? It's very interesting. So this is the simulation of the external electric field around the head. And I should say that my take on AI is domain-informed, so domain knowledge. There's no black box. It's maybe gray box, but no black box, and we need domain knowledge. So we have the biophysics models we have developed in our lab of head, the whole upper torso. When we want to simulate the EEG propagation, I've never done any research by trial and error. We have full biophysics model. It tells us where to put the electrode. That's what we do. Okay, so this is the external electrical field around the head, and that field grossly affects the normal scalp EEG. Look at this. So if you go only 8 millimeters or so into the ear canal, the strength of the external electrical artifact, so when you have artifact, you have to throw away data, diminishes. So after 8 millimeters inside the ear canal on your earplug, the effects of external interference are gone. So why is that? And all of you know the answer, it's just not obvious. So the ear is a cavity surrounded by conductive tissue because skin inside is conductive. So what is a device which, if you have conductive enclosure of anything, that's called a Faraday cage in physics. And that Faraday cage basically grossly attenuates the external field. So the ear is effectively a nature-built Faraday cage. Okay, so with that, we can take this lovely chap again, and on the left in red, you have scalp EEG. In blue on the right, you have ear EEG. And this is several sleep activities. This is deep sleep, N3 or delta. This is the K complex, and so on and so on and so on. I would like you to observe that the red and the corresponding blue traces are very, very similar. They're never going to be identical because no two EEG electrodes are identical, but they're very similar. So with that, and with our device, with the electrodes, photoplethysmogram, electronics, and so on, so this elderly person can be diagnosed at home. He can simply put that in his ear canal, and he can be treated at home. Okay, so this is maybe if you click on the video, the top is scalp EEG. It doesn't work when it should. Never mind. The top on the video is scalp EEG, the bottom ear EEG, and it was supposed to run a video in real time, but it doesn't work. Okay, next slide, let's see if we can do that. So the next thing is, I said my title is Doctorless Hospitals, okay. I believe that it's a waste of time to go to a GP. You wait for several days, by which time your symptoms will be gone. They do a very basic check. They check your maybe respiration, temperature, look at you, maybe tongue, whatever, nothing much. Then they refer you to a specialist. You have to wait again. The specialist says, okay, now you go to take blood, take electrocardiogram, take this, take that. So in 2 months, by which you have all the parameters, your illness is gone. So how about the cardiac illnesses? Because cardiac illnesses are the biggest killer across the world. So to examine cardiac illnesses, previous slide please, to examine cardiac illnesses, we have built the whole biophysics model of the upper torso. So you can see that even the tiniest detail like the oxygenated blood and deoxygenated blood with various amounts of hemoglobin have their own electrical and magnetic parameters. So with that, we then simulate the propagation from the heart, because heart is an electric dipole which rotates here. So here you have the standard chest electrocardiogram, and here you have the same electrocardiogram on the head. So I'd like you to play the video, please. Oops. Not exactly the video I wanted, but maybe. Okay. So on the bottom left, you have an arrow, and if you press it, the video starts. Okay, the video has started. You see that the electrical signal propagates, and stop. Stop the video. Thanks. So you have seen the propagation of the simulated propagation of the electrical signal across the body. So at the time of the R peak, when the heart muscle fires, you see that you have a huge electric potential across the chest, meaning you can indeed record electrocardiogram across the chest. You also have huge electric potential difference between your arms. So this is why some of you have ECG watch. You have one electrode beneath the watch, and the crown is electrically insulated from the rest. So you bring your finger, and you stay still for 15-20 minutes, and you have electrocardiogram. But potential difference across head is very, very small. That is because we have empty cavities, so the windpipe, mouth, sinus cavity, which prevent the propagation of the electrical field related to heart to the ear canal. Next slide, please. So can we still do something? So on the left, you have a simpler simulation. You see that there is still some potential difference between the left and right side of the head when it comes to the propagation of the electrocardiogram. Can we play the video, please? So on top, you have electrocardiogram from chest, a bit compressed in time. On the bottom, you have electrocardiogram from the ears. What you see is 1,000 of some units for chest and 20 of some units for ear. So the ear signal is 50 times weaker than that on heart, on chest, of course, because of these cavities. But when you do a little bit of processing, and let's not call it AI, but let's call it processing, this is the cardiac cycle from chest, and this is the cardiac cycle from the ear canal. You can see that they're almost identical. So with that, we can get full clinically valid electrocardiogram from the ear canal. So these are some of the breakthroughs which came from my lab. So we have patented ear electroencephalogram, we have patented ear electrocardiogram, but we can do more. Can we switch that? Oh, I can do that. Okay. So now we can monitor brain. We can monitor heart conditions. How about pulmonary conditions? So the pulmonary conditions are the second biggest killer of humans. Especially as dangerous the chronic obstructive pulmonary disease, whereby for you it's very easy to inhale, but very, very difficult to exhale. And many of you have smart watches. Smart watches are basically sensing is based on the photoplethysmogram, which is a set of LEDs which shine light through your skin. The reflected light is recorded, and you can get some parameters like respiration. Ironically, the wrist photoplethysmogram is the weakest signal you can ever record in terms of the optical signals from human body. So when you go to hospital, they record your blood oxygen levels from the finger. But from the wrist, it's almost impossible. This is why smartwatches are not accurate. So please don't trust them. Whatever they tell you, that's not true. The only way to have a signal which is half decent quality is to stay still for 15-20 seconds and wait for something. If you compare the very, very weak optical signal, photoplethysmogram from the wrist with that from the ear canal, you can see the huge difference. So the ear is indeed a phenomenal source of information related to your state of body and mind. So with that, and inspired by COVID, whereby the patients infected by COVID, they experience very low blood oxygen levels, but it is not followed by, accompanied by breathlessness. For us, if we have low blood oxygen level, we are breathless. So you can tell. For COVID patients, you can't. Another problem with the wrist or any other outer body location for optical sensing, and maybe is that the problem of vasoconstriction. So what is vasoconstriction? Human body, the temperature of core human body, the core temperature of human body is 36.5, 37 degrees. Here is maybe 21 degrees. So my blood vessels are constricted in order to cope with the temperature. If I was to put a sensor on my skin, optical sensor, the readings would be biased because it wouldn't be the core conditions of my blood vessels. So think about temperature. You never record temperature from here, or from there, or from there. It's always places which are concealed, like armpit or arm or ear canal. You can record temperature from the ear canal. In the same way, the PPG photo signals recorded from the ear canal are not subject to flux dissipation, and they give very, very accurate measurements. And you can see here that so the subject was breathing normally, and they stopped their breathing for 30 seconds, these pink areas. When you stop breathing, then blood oxygen level goes down. Okay. So this is for the in-ear sensor, and blue is for the finger sensor. You can see that the readings are different, but now we know that the only correct reading is from the ear canal because there's no vasoconstriction. And the second, the ear signal is faster. You see the dip in blood oxygen level, it's faster than than that from the finger. And it goes up to 25 seconds. It's the difference. So it depends on the size of the human body. So now we know that we can also deal with respiratory diseases using hearables. Dementia. So dementia is a very, very big problem of modern mankind because luckily we live longer, but it's accompanied often by various diseases like neurodegenerative, like dementia. So the keyhole to the brain is basically electroencephalogram. That's the only keyhole to the brain. On the other hand, it's very interesting to look into cognitive load because dementia patients respond differently to cognitive load than normal subjects. To deal with cognitive load, people usually take the fMRI, functional magnetic resonance imaging, but that's extremely expensive. So luckily for us, the carotid artery, the artery which supplies brain with blood, passes by the ear canal. It brings oxygenated blood to the brain, and these kind of red spots here are due to the oxygenated blood on the brain in fMRI. So using simple photoplethysmogram, simple sensor on the earplug, we can then at least gauge the cognitive load of a patient together with their electroencephalogram. So we can really make a breakthrough in dementia. And the agreement between cognitive load from in-ear sensor and fMRI is maybe 92, 91, 97, whatever. It's very, very significant. Okay. How about blood glucose levels? So if you shine light through your skin using photoplethysmogram, so you have 3 or 4 different wavelengths of light. If you use the red and infrared light, the combination of their reflectance gives you information about glucose level in your blood because the light reacts, infrared light reacts to glucose, red light reacts to glucose. So we have been able to produce a blood glucose meter using PPG. Now, we know that with hearables, in-ear sensing, we can monitor electroencephalogram, electrocardiogram, pulse, respiration, blood oxygen level, blood glucose level. What else do we know? What else do we need for a doctorless hospital? Well, we need reliable data because, as you can tell here, although I had sufficient data for proof of concept, my number of data points is very, very small. Which brings us back to Denis Gabor. So Professor Gabor had luxury in 1940s, 1950s to derive his theory, put it on the shelf, and wait for 20 years for somebody to produce monochromatic laser light for him to prove his theory. We don't have that luxury now. So part of my work is also to produce our own electronic devices which work with our hearables. So this little thing here is very, very powerful. It has a microcomputer. It's less than 2 centimeters in diameter, and it can be part of an earplug. So one of the slides I particularly like, and is talking about the engineering development of an engineering idea. Okay. In terms of functionality, whatever you have here, all those wires, all this thing in the lab, is equivalent to what you have there, a device with electroencephalogram electrodes, electrocardiogram, a PPG, accelerometer, temperature sensor, whatever. It's equivalent. It's just that this works in the lab, and when I have this, I'm very, very happy with that. But I cannot go out to the real world with that. So it needs several years of technical refinement to package it up into something which is ready for the technical world. And this is basically almost everything I wanted to tell you, but I have a few more slides maybe about AI and medicine, because this is the biotech forum. So despite all hype, recently in the MIT Technology Review, which I trust, there's a big headline: hundreds of AI tools have been built to catch COVID. None of them helped. And that's true. What helped is that people developed antibodies and so on, a bit vaccines maybe. But AI tool does not help. So AI is not almighty. The second thing, there's a huge push into investment in AI for health. So a colleague from Oxford University by the name of Baptiste Vassi conducted a piece of research. So he looked into, up to 2022, he looked into 140,000 articles in PubMed, which is a repository for medical articles. So he looked into every article which was tagged AI. So anything to do with AI. 140,000 such articles, 136 or whatever, up to 2022. Out of them, only 81 was proper clinical study. Only 9 were prospective, meaning following patients after. Only 10 had randomized clinical trials, and only 2 were fully published. So, put it into perspective. So, despite all the hype about AI, out of the 140,000 published study, only 2 were credible. And I don't know if either of them found clinical application. So let's be careful. Okay. So what's the solution? Well, I'm an engineer, so my solution is to approach the problem with an engineering mind. So what is the engineering mind? So AI, especially kind of buzzwordy AI, which comes from media hype, promises to mimic the human brain, mimic the nature. I'm sorry, we cannot mimic that. Because people, humans, they learn from very, very few examples. When I was a little kid, I burned my finger when my mother was making coffee on the hub. One example, I never again put my finger there. For AI to learn that, or robot to learn that, you had millions of times somebody burning their finger in order to train the AI not to do that. Okay. So the second thing is talking about mimicking nature. So if we were mimicking nature, we would have made an airplane to flap the wings when they're flying. The airplane doesn't flap the wing because the engineers have put powerful engines beneath and we fly. Okay. So how about using same principles when developing AI for health? So going back to domain knowledge, in engineering, physics, biophysics, materials, we have domain knowledge. For example, in what I do, I never do my research by trial and error. That's heuristic. Trial and error is pre-scientific. Okay. There's nothing wrong with pre-scientific. The Egyptians have built their pyramids in a very, very pre-scientific way. They couldn't calculate everything about those pyramids, but they found a way through experience to move those stones and build a pyramid which is still there. But we cannot afford that any longer. So in my research, we have, again, very, very precise biophysics model of human body, and we model the propagation of such signals. To the extent, so we put the electrical and magnetic parameters of each tissue, to the extent this red here is the little air pocket in the cervical spine. So the neck spine, cervical spine, has a little air pocket which alters propagation of signals. We model all that, and with that, we bring domain knowledge into what we are doing, which means that our AI model can be smaller, can be physically informed, and can be much, much, much less of a black box than models which you normally use. Going to something people often talk about, in modern AI, people say, I have an end-to-end solution, by which they mean I bring raw data in and I have raw data out. I'm sorry, but I don't know where a mobile phone is, but that's an end-to-end solution because mobile phone gets data in and it gets some data out. Nobody calls it AI. Okay, so this is our own end-to-end solution from the physics of the propagation of signals through body and head, through our device, the interface between electronics and skin, to all these kind of sorts. We have an accelerometer here, all sorts of artifacts like when you are walking, talking, and so on, so on, so on. And with that, you can do various things. With domain knowledge, for example, in our very tiny AI models, you can record the scalp electroencephalogram. So this is the brain signal from the head. From there, we can extract perfectly good electrocardiogram. This is clinically valid. So that type of magic is only possible with domain knowledge and models which don't overfit. So AI on the edge, tiny AI, small AI. Okay, I think that it's almost the end of my presentation. I would like to kind of round off. So with domain-informed AI, no data is bad data, because if I have artifact due to chewing, for example, if you chew, you can test that your ear canal is a bit moving, so you have artifact in your EEG or ear ECG. And this is the artifact. It's a very, very large artifact, and normally you would have to throw away such data. But on our device, we have accelerometer, we have many other things which record the artifact, so we can digitally remove it. If you look at the artifact due to the chewing of banana, grape, Coke, or water, they're all different. So not only I can clean my signal, but my artifacts tell me what I was doing. For example, I was drinking water or eating banana. Or you can tell me how much calories I've taken in, because each of these is different. The patterns are different for each of types of food. Okay. Stop calling everything AI, but don't stop developing AI. Okay, we need to develop AI. We need to do it in a very, very responsible way. So human computers have not suddenly become intelligent. They've just become bigger, and we can run bigger and bigger programs on them. But they can augment human intelligence. And we are maybe on the brink of having something historical. So we can have a human-centric engineering discipline, which is the AI. Okay, with that, doctorless hospitals. So everybody is different. I am 183, I don't know how many kilos I have, but more than 90. And person of much younger than I, but adult, go to a specialist, we suffer from something. So we are both adults that give us same prescription. Take something 3 times per day after meal. Okay, maybe I'm 30 kilos bigger than the other person, or maybe 20 centimeters taller, and my eating patterns are very different. So they treat us in the same way, especially for chronic conditions. That's very, very suboptimal. All these sensors I have described on the earplug, they can monitor the state of your body and mind. So you can monitor the intake of medicaments. So how my metabolism is very, very different from when I was 20. And I will be prescribed same thing. So this can tell you how your body is absorbing those medicaments. You can have fully personalized medicine, and we can maybe move to the era of AI. With that, thank you very much for your attention.